All right, hi everyone. I'm Eduardo Cotilla-Sanchez. I work also at Oregon State, faculty on energy systems. My expertise is power system protection. I like to say that I'm a modeler of bad days. If I had to summarize my research in one sentence. In my teaching, I collaborate with Ted and all the members in our group, and I'm in charge of the power system sequence. So in the fall term, I teach 75 students, senior level, undergrad, power system analysis. So what everyone should know about power system, power flow. Then in the winter term, I teach power system protection. And then in the spring term, I teach smart grid. So that's kind of my teaching parallel life. So today I'm going to be talking about power system protection, microgrids, and clustering. And really, if I go back to the end of Jinsub's presentation, just to pick up there, he was mentioning that DOE wanted us to look at risk and assess risk. And we use computers many times to work on simulation-based assessment of risk. So kind of the back in your mind topic for my whole talk is how do we get all of these topics that we have been looking so far and try to model them in the computer to get answered with models that make sense. So that's going to be the overarching scheme. And then I will focus in kind of the things that they are really difficult to put in the computer. If you look at microgrids, if you look at islands, if you look at zoning and protection configuration, those are the ones that they are really tricky to put in power system models. It's not just the nominal case that we run our power flow n-1 times and we are happy with that. Everything converges very nicely and our equations are very well behaved. This is when the math is not very well behaved. So just with that in mind, a little bit about models, then that topic in microgrids. A lot of my research involved cascading failures and cascading outages. So that's a little bit of the motivation for some of the research. Then we'll look back at some examples about microgrids to switch out from research to applications. And then a little bit back into research to look at, okay, knowing all of this, how can we actually implement all of these concepts and simulations into actionable items or strategies that an operator can work with. So this is not a very good resolution map. That this is the Western Interconnection. And if we look at all our assets and looking at, okay, how do we measure risk? We need to kind of like do a selection of what are the things that we're going to put in the computer to run all of those simulations. Here in the Western Interconnection, we have 20,000 buses. What do? Do we get every single voltage that we have? Do we go all the way down to my dishwasher voltage level? What do I do in order to put it on the computer? So really there's a lot of people talking about modeling, and you probably heard that quote that says, all models are wrong, but some are useful, right? So how are they useful is how do we ask questions to that model, and we cannot expect to get every possible answer from a single model. So in this case, this is just an example model that we were working on our wave energy project, trying to look at the integration of the PMEX set, the South Energy Test Site, planned to be 20 megawatts into our power system. So if you look at this model, we are looking at wave energy converters that they will come out in these 4 cables, 5 megawatt each. And then it sounds pretty ridiculous, but we got a whole Western Interconnection model basically collapsed into 5 different buses. That sounds quite outrageous if you're looking at things like power flow models, but in this case, we are really looking at the interface. So we were looking at low voltage right through, protection configuration, harmonics. So in that case, we were able to just say, okay, I'm gonna focus on that WEC, and this is the answers that I'm expecting that model to provide. So just an example of that case. In the literature, there was many models that they are very appealing because they are very simple. So if you look at things like social networks, a lot of people look at things like the 6 degrees of separation. There was a very famous paper that got into Congress because it was basically saying that if you are looking at different substations, you should really, to have an adversarial attack, you should attack substations with very low flow. And it seems like a crazy idea, right? Because you would not have a lot of impact if you are hitting substations that they have a very low, they call it traffic, but basically flow through that substation. So the main mistake that paper was encountering is that they were using a model for the network that was not even power flow based. It was just looking at basically a social network model, a domino model, where you say, if I break, then my neighbor is likely to break. If I break here, then the next one is likely to break. And that's not how electricity works. So if that's the case, if we look at damage in that way, so if we look at damage, I just have here a y-axis. This is actually a simulation done with the Eastern Interconnection, so 65,000 buses, the whole East Coast. And I'm looking here at impact. So sorry about the axis, but here in the x-axis is basically how many hits I'm taking to the network, and here I'm measuring the impact of that network. Looking at that topology measure, if I hit one substation, two substations, three substations, the best strategy that I can have is actually to look at betweenness. So I need to hit at the substations that they are very central. That kind of makes sense. This one here, the 0 here is just an average, so it's a random attack, blindly hitting substations. And then this yellow one for comparison is the one that paper that got to Congress basically was proposing, to do attacks to counterintuitively very low flow substations. So you actually, if you are the bad guys, you're actually doing worse than attacking at random, right? So in this case, we were trying to show what is the importance, right? Congress was freaking out and say, how do we protect substations? And now we're saying, oh, this is how basically the average path length increases, right? This is the number of the degrees of separation with Kevin Bacon from your substation, right? So if you have 0, you can reach 6, with 6 hubs, you can reach Kevin Bacon, right? If you keep hitting, then your substation, it's less likely and less likely to be friends with Kevin Bacon. So the network is damaged. You should be closer to him, right? So this is just one strategy. Betweenness worked very well with that model. Now the second one that we ran was a little bit more toward power system. We still didn't run a power flow, but then we said, we're gonna count number of generators and then number of loads, and see how many times we break the path between generators and loads. Same simulation here. The best that we could do if we were the bad guy to do that number of attacks was the degree-based attack. The degree of a substation is the number of lines coming to that substation. So 3 is 3 lines, 4 incoming lines. So with this model, looking at percentage of sources and loads that we disconnected from the network, the best that we could do was actually to try to hit just substations where we could be counting the number of transmission lines. Keep in mind that the strategy of minimum traffic, it's still doing very bad, worse than random. You know, if you were an adversarial attack and you don't know how to run power flow or you don't know anything about power systems, this is the best that you can do at random. Actually, the shadow is the standard deviation of random attacks. So don't worry, I'm getting to a power flow based model. So this is just running your power flow and see, okay, I'm removing substation, kind of doing like n-1, n-2, and seeing how much of the network I'm able to keep alive, how much load I can keep alive. So this is just basically looking at blackout size, percentage of my load that it's still being served. And then the best that I could do, and actually I could damage very badly if I look at an actual power flow model, is looking at basically max traffic. So the best that I can do as a bad guy to cause damage is to look at a substation with a lot of flow through that substation, and that should be the first one that I need to hit. That seems like very obvious for if you are used to running power flows, but there was a lot of papers that don't even consider a power flow based model for this type of calculation. This one is actually a DC power flow, so we're not even going crazy with AC, anything OPF or anything like that. Just a very simple DC approximation. So in this case, not surprising, that proposed approach to say, okay, if you really find some obscure substation that has very, very low flow, that's very likely to give you a super large blackout. That's not very likely to happen if you're using that model right there. Any questions so far? That was just an example of models. Am I going super fast? You want me to slow down? Okay.
Negative blackout percentage.
That was the 0 was the average as random attack. So minus 10% was that in average, the attack will give you 10% more load than even the average random attack.
Okay. You got to try really hard.
Yeah. Yeah. So if you were a bad attacker trying to be good, or something like that. So this is one of the reasons why those models, they really don't work. If we look at the blackout in the Western Interconnection from 1996, when we look at cascading failures, we like to look at the sequence of events. So in this case, look at the events that were generators or transmission lines coming out of service. The first event happened right here. Then the second event happened relatively close in terms of topological and electrical distance. Then number 3 was also relatively close. So very likely that you will be in the same RTO or you will be in the same balancing area. Very likely that you will be aware of those things happening. But then where do you find number 4? Right here. So that was number 4. And then you don't have any sense of locality anymore because things basically travel at the speed of light. So timing and distance are some of the things that they are very important to include in those models that we are going to ask, what are the important things that we need to protect? So we've seen this multiple times, and that consideration is very important for resilience. So keep in mind those two ideas, how far or how close we are from our assets, and also what is the timing of those events happening. Is it operator time? Is it lifetime? What are the timing of that sequence of events? Another ingredient that it's also very important to put on the model, together with timing and distance, is what type of loads are we going to be considering. We have a very good knowledge of generators when we put it on dynamic models, for example, when we are trying to look at time domain simulation, but sometimes we don't really pay a lot of attention to the load. Just to show how important that is, in this example, you can see a lot of the times the easiest way to break a power flow simulation is just split into islands, split into microgrids. Then things will go a little bit crazy, and then it's very likely that we're going to find cases that they do not converge. Sometimes commercial simulators, what they do is that they convert all of your loads to constant impedance so that they have a nice, smooth function so that you can go and really solve very highly of nominal operation. But that sometimes is not the case. We can now model everything with a constant impedance. So just to show you an example here is a simulation where we have some protection event where we're trying to divide the system into 2 islands, into 2 microgrids, if you want to call it like that. So in constant impedance load, everything converges and we have a flat hello world, kind of like, okay, things are coming back to normal. Constant current load, in this case, also gave us convergence of those 2. If we did constant power, which is very easy to run because that's the same constant P and constant Q that we run for quasi-steady state power flow, actually we do not have any of the 2 islands converge because we are very stiff in voltage and we might have some voltage collapse or some situation. If we have an exponential profile for the voltage, so one of the things that we did is like, okay, you might have just a constant power, but then how about adding some exponential decay so that when the voltage goes down, we are going to remove a little bit of that voltage, so just including some exponential constant. If we added a little bit of that exponential behavior so that it smoothes out that function and our equation and our Jacobians can actually find a solution, then one of the islands actually converged, but not the other one. The other one still was a solution that we were not able to find any physics that would agree with that. So load model, I'm not going to do a lot of emphasis on that later in the presentation, but it's one of the other ingredients that sometimes we might really have to highlight for our time domain simulation. Protection devices, also very tricky sometimes to find out a baseline of, okay, how are we going to model that type of relay? How are we going to model the delay in all our relays? So some models that we put, this is just a link to an open source simulator that we developed at Oregon State, and it's a time domain simulation. So it's free open source and it's on GitHub. It's a time domain simulator, so it does a lot of the things that you can do with PSSE. The nice thing is that you can break it down and you can find code that I wrote when I was a student. It's very crappy. I don't know even English back then. So I was tempted to put my variable names in Spanish, and my advisor would say that I was crazy. If you want to download it, and we have some students, Ted and I, we have co-advised some students really working on a lot of the load models there. So you can just run it and say, we have a large Poland case with 2,300 buses. You can just run A-1 simulation. You can just decide where to break things down, and you can get those output profiles. You can break it. You like to break things, so just break that code and let us know if you like it. But one of the things that we have in that code, it's a lot of the relay models. So we have distance relays. In this case, instead of having just a static threshold, if you're looking at relays that they are telling you how far you are from the threshold, it's really tricky to combine that with, for example, a commercial software like PSSE, because you have a fixed step integration size, so a step size. So it's very hard to integrate things that we know about relays and match those with how sometimes commercial software are doing the math in your integration step size. So in this case, for example, if you have a fixed step size, that's very limiting to relays that could trip anytime. So then you need to go back and see what actually happened in reality between the time that the relay will have tripped and the next time that you decided to solve your equation. So in this case, the way that we address that in our simulator was try to do a variable step size. So if things are happening, we just slow down and integrate all what my relays are doing. If things are flat and there's nothing interesting, we speed through so that we can gain some time, because time domain simulation is very expensive. So that's one of the things that the student that Ted and I were co-advising on, he was working. So he spent basically his PhD validating this model with the output that you will get from PowerWorld, CMM PSSE, and try to show that it's faster and that you can break it down. So this is an output simulation that we got from that Cosmic simulator, and we tried to reproduce, if you look back at that map that I showed you from 1996, that concept of things being non-local, that's something very important that should show up in the output simulation from your outages or from the events that you are modeling. So in this case, this is supposed to be Poland. Polish power systems engineers are very nice, and they publish the whole country as open source. There's several snapshots. This one is from 2003. It's a winter peak with 2,383 buses. You can also find 3 other snapshots from winter peak, off peak, summer peak, off peak between 2003 and 2004. So I work with the IEEE work group in cascading failures, and we really like this model because people are starting to understand what the model behaves like. So a lot of the simulations are done either with RTS 96, which is 73 bus system, or this one for larger, kind of more real life test case. So here in Poland, we were simulating these 2 black lines is an N-2 event. So we took out 2 transmission lines that they were somewhat critical. And then you see the sequence of events still with the number. You see that number 1 is the next line that came out. Number 2 was right here. Number 3 was right here. So you start to see how the output of your models is matching not just the cascading or the blackout size in terms of percentage, but really where things are happening. They are non-local. All the squares here are the load shedding relays. So there was a location where the simulation was shedding load, and you can see that it was going like crazy. There was these buses here that I don't know where that really is in Poland. My Poland geography is not very good, but that seems a little bit far if this was a topological representation. And they were shedding load. So we were able to reproduce that. This blue or teal, there was a microgrid that was generated there, or an unintentional island that actually survived this whole event. So a lot of load shedding all over the place. But the one thing that I want to bring your attention to is here, that there was the other aspect. So the aspect on geography, and then the second aspect was on that timing. What is the timing of those things? So sometimes when we look at all of these large events and we look at what is the timeline, what is really the wiggle room that we have for actions, for example, or how much we can look in terms of actions, or really how much this is computational time. How much time do I have for my computer to tell me something else what to do, so that I feel good, right? So that the computer is telling me to do this. Or is helping me or to have a situation where I can get an answer. So really having that timeline, this is seconds, so this is 150 seconds, 200 seconds. You can see how these are just the branches that they are coming out. At the beginning, they're happening basically 100 seconds apart. This is a slow regime of cascading. If you look at the timeline of many of the events that have happened in large events, there's a very good agreement between the first stages of cascading, giving you this timeline, and then the later stages of cascading, giving you basically a few seconds in between them. So getting that information just from the analysis is very important to see before you can even think of any actions. This is basically giving you a budget of where to invest that time. So those two aspects for any kind of simulation, very important.
Is it possible to predict what substation would blow given that one at the beginning goes? Or is it all?
Yeah, so in any kind of a cascading simulation, you are not going to get a lot of information just from one cascade. So the type of simulations that we are doing are basically Monte Carlo sampling of many of them so that you can start understanding where are actually the critical lines that they are involved when we have trouble. And there's many ways to sample that. I have some colleagues that they actually develop a method to do that sampling the same way that you look for cancer markers. So combinations that they are very critical. So imagine combinations of 2 or 3 transmission lines that they are basically bad, cancer level bad, right? So they look at kind of those interactions. They use computational algorithms that they are sometimes based on biology because we learn a lot about their big data problems. So did that answer your question?
Yeah.
So really, this is just one cascading path example, but we could really compound that in a lot of different ways, depending on what we are looking at. So just to do a little bit of emphasis here, I'm going to switch out of research a little bit to focus on microgrids and why they are so difficult to model sometimes and to see what we are doing with them. So just going to that portion of microgrids and whether we can use microgrid as something that could be a tool to mitigate those kind of events, or it's something that's going to affect us, right? One simulation that we could do is say, okay, what are the cascading paths if I'm already starting with systems that have a lot of microgrids, right? One of the things that we always find in any microgrid definition is that we're going to have 2 modes of operation. Either we can have a microgrid operating in itself, or it could be grid connected, right? So really, when we are looking at this resiliency or big event applications, we are looking at those transitions between grid connected and going to a microgrid, because that will give you a large percentage of load that survives, perhaps. This is just kind of like the complexity of what you will have to put in the model for a microgrid. Imagine that we're talking about how to put in that model a lot of the relays, a lot of the different elements that you will have just as a regular substation. Now it seems that you have to zoom in and see how each one of the elements of that microgrid is going to have to behave. So just to have in your mind, how many extra equations do I have to add, right? Do I have the controller from my exciters, from my governors? Do I have all my controllers from my relays? Now I need to think about how many equations can I add that they're gonna do my microgrid central controller, for example, to see what voltage output I'm putting out from that microgrid when it's being islanded. So just a little bit of the thinking about what is the computational complexity. When things are connected, we like to think about what is the voltage control of that microgrid. It's not really that simple distinction that we had before in the simulation where we say we have a PQ bus, we have a slack bus, or we have a PV bus, right? Now that PV bus, it's controlling the voltage in a very particular way coming from that microgrid. So we need to change those equations there. Now, if we go into islanding mode, remember that graph that I showed before with those load models? Now we need to figure out what is the frequency going to behave like when we go to that islanding mode. So we are focusing from voltage control to now thinking about what's really the active and reactive power mismatch, and how is the frequency health going to be on the microgrid or in the island when we disconnect. This is just one of the equations that we should add, some droop control to those controllers in my microgrid. Some of the examples that we have from success in microgrids: in the US, we have a lot of the military application and demonstration projects. One of the first one was the Spiders project. I don't know if you're familiar with the Spiders microgrid demonstration project. I was at Sandia National Lab as an intern when they were working on that project. And we thought that it was very amusing because everyone in the project had the name of a different spider. My manager was, one of them, and it was fun. So I follow very close to that project, and I'm familiar with some of the demonstration. But here, looking at earthquake, we were just looking at another good example of really microgrid data from some events. There was a few demonstration projects in Japan in particular. This one is these Roppongi hills. I think that's close to Tohoku hills. They have a really nice financial area right there. They have a nice Hyatt, and it's one of the areas that have a lot of consumption, a lot of peaks, because there are some of the financial buildings, and then maybe over the weekend. So it's a tricky load profile, in my opinion. So they have some data from these electrical systems in the Roppongi hills. They have a 6.6 kV distribution cable. Their distribution automation system in Japan, they are amazing. I was visiting one of them, and I was feeling just kind of like in a science fiction kind of movie. I didn't understand a lot of Japanese. I have zero Japanese knowledge, but I realized that after all they were talking, I understood hydrogen, right? When they say they say hydrogen, and they say in English, right? And I say, oh, and also pipeline. So they say, half an hour of Japanese, and then I heard pipeline. So I was super excited that I understood something. It was in English. So, but the distribution automation system, they were very, very well integrated in those urban areas. So I think they were able to get really good data from some of the events, like the earthquakes. And they basically, what they learned, this is just describing this graph here, is that this is kind of their nominal operation. And then when the earthquake happened, they have a frequency excursion, but they have a good backup of gas. So they kept operating the microgrid for a longer time. So really, this is the kind of frequency excursion, 50 hertz, and then it went to a little bit under 49.8, I think 48.73. Continue for a few minutes and then recover, and the microgrid islanded for several hours. So they were just looking at, really they can enhance resilience, and then you really need to be careful at these transitions, how are they gonna be behaving. So the type of simulation that we had before could look at things like low voltage right through, what are the frequency excursions, how are the controllers and your relays behaving, and then do you really have a lifeline supply for your local sources. That's one of the things that they learned. And a different scenario, this was a Sendai microgrid. Basically what we learned from there is that the same thing happened. They had some critical loads that they were able. They didn't have enough supply from their, I believe this was the natural gas sources, but they didn't have enough for all of the loads, so they were able to provide some of the critical service. So they have some gas here, March 11, everything was grid connected. Between March 11 and March 12, they had some of the grids, well, this one went into voltage collapse. The gas was still disconnected here, and then the DC was on battery, and then this was kind of the chaos period, I guess, in my opinion. And then they were able to get the gas running for supplying at least some of those critical loads for basically a day and a half or 2 days until they were able to recover. So really, besides those transitions are very important, and instead of waiting to, or go back in time to 2011 to see how we could improve that, it's really very important to be able to simulate the time domain behavior for those microgrids on the computer, so that we can optimize what's happening during that period of time. Now I'm going to switch to the last portion of my presentation, where I'm going to go into, okay, we saw that we will have some budget to do some sort of operations. What are the things that we can do so that we can make that transition, like in that microgrid, very smooth? Out of what we can learn from sampling very, very many events. One of the things that we can do is load shedding. It seems like a really good idea to implement, because we can just look at even doing something very naive and homogeneous, like, okay, we're going to shed a lot of load in multiple locations. That's very easy to do in the computer. Then we can also select other options, like, okay, we can do a priority like they were doing in Japan. We can look at what is the distance between those loads, trying to look at what the map is doing and say, okay, maybe you can improve my voltage profile if I'm doing my load shedding in a location that is closer to where bad things are happening. There's many heuristics that we could do. So the benefit is that we can basically put all that in real time. They're quite simple operations, but then we do have a direct customer impact if we don't do the right choices. So that's one of the things that we can put in order to improve that profile, that transition in those budget chunks of time that we saw in the simulation. And the other thing that we could do is islanding. So in this case, it's basically an intentional creation of microgrids. Usually we would just compute those offline. We have the knowledge of how do we want to split the system, and then we can say, okay, we could form those islanded microgrids depending on many things like slow coherency. We can just put fault and see how the generators swing together, and then they are likely. That's how Hydro-Quebec was doing it at least a few years ago, last time I checked. They look at electrical distance. You can look at active and reactive power balance, many different options. It's good because we can leverage all those lifeline sources that we have, and then we can isolate the sections that were not in trouble from those that they actually were. Like if you look at the Poland map, maybe those folks that they were doing load shedding, they should just stay and not do anything, or just island and keep operating. However, that calculation of areas or potential islanding and microgrids it's slow. So one of the things that we worked on to make that decision is, okay, think about having that period of time of 100 seconds between one event and then the next transmission line. What could be the sequence of decisions that could give you a good solution? I'm not going to go a lot into the math, but a tool that we use was the Markov decision process. So an MDP that's telling you this is just a state of what we have right now, and then we can take different actions, and it's going to get me to a different state. So it could be now I'm in a healthy power flow state, dynamic simulation state, and now I can go to a marginal state, or I can basically get in trouble. So there's a policy that basically if I say the reward, I can measure a reward like we did it at the beginning of the presentation and say percentage of loads that I'm still serving, that's going to be the reward from my computer calculation. So the larger that number is, if I want to put it in per unit from 0 to 1, so 1 will mean that all my load is being served. 0 will be a complete outage. So I can play with that reward number to try to calculate the risk essentially of taking those actions as a way of doing a heuristic control. So we will go, and there's a very nice computer science result. I'm not a computer scientist, but I like to hang out with them because they have a really good way of proving things. And I really like this result that said that, okay, imagine that Pi 1 is just your policy of just doing load shedding. So you're a power system operator, your favorite thing in the world is do load shedding, right? So that's like the one thing that you know how to do and the one thing that you know how to calculate. And then you're a power system operator type 2, which your thing is really to create microgrids. right? That's the thing that you go for lunch and then you just microgrid everything, you know, and this is like the one thing that you know how to do. So there's this theory in computer science where you are looking at automated, this is all in the framework of automated planning. I didn't mention automated planning in this talk because in our power system world, planning has a very different time scale. For computer scientists, automated planning is basically automated control in a shorter time scale. So I'm still talking about seconds, those 100 seconds of budget that we have. So the nice thing about some of the results that they found in this control is that there's a policy switching strategy that says that even if every time that I check, let's say my simulation, of every time that I go back to my visualization interface and I look at what's going on, or I get my power flow equation, even if I switch to the best that I can do at that time step, so even if I go and then say, oh, I look at here right now, and just looking at my limited horizon, this is really what I can do. Even if I just check every time and I switch to the best that I think I can do right now, that policy switching guarantees that I'm gonna do at least as good as if I had calculated the whole horizon from scratch. And I say, I'm gonna do an islanding here, I'm gonna do a load shedding here, and then I do islanding here. So I'm gonna be able to get at least as good of a sequence as if I was able to calculate the whole horizon in one shot. So that's a really good, I think that's a feel good kind of thing that you cannot really mess up very badly, no matter what choice, if you are kind of like following that input. So there's a few caveats to that theorem. It's not universally as a guarantee. That solution assumes that you have an infinite horizon so that you can look at always at the end of the simulation, but maybe you don't have enough time to simulate the whole thing. So you can say, I'm gonna simulate the next half an hour, and then this reward will have some discount factor. But even with that limited horizon that you can look forward in time, it still works very well. So what we did was just to put this simulation, we did this version of the simulation before we had the open source simulator. So we actually ran it talking to PSSC. So we did a Python script and then automated the calls to PSSC, treating PSSC as basically our true power system horizon. Since this work, we actually put it also in our open source simulator, so it's easier for us to see what's going on. But basically we had PSSC, we got a case 39, so something a little bit smaller, power flow, and then we caused random n-2 contingencies, and then we were doing every time step, we either had grid checks or relay check. And then every 5 seconds, that was our kind of emergency dispatch time. So we have our simulator running, and every 5 seconds, it's kind of like, okay, we open our eyes, see what's happening, and see what control actions or emergency actions we can have. We can do that with any time horizon. That's just one that we thought it would work with this synthetic test case. So in this case, we say, okay, what we can do is we get this IEEE 39 bus case with 10 generators, 39 buses, 19 loads, and 46 branches, including transformers. We put it in n-1 secure form. You'll be surprised how many test cases are published and people use it for a lot of research and simulation. They are not even n-1 secure when you first get them in terms of line limits and things like that. So we initialize it into n-1 secure, and then we say, okay, let's try to set up what we would think that it will behave well as microgrids or islands if something bad really happened. So we check balance of this first splitting into 1 and 2. So we split the system in half, and then we split that roughly in half again into 1, 3, and then 2 and 4 again. So that was like one of the strategies. Just split in half and then split in half again and see what happens. So there's a lot of numbers here, but basically the question is, how can we do better? So if you read from top to bottom, you have basically 3 chances to do something. The first one is, okay, can I do islanding and then islanding? Then I'm done because I only have like basically 2 options. Then can I do load shedding and then load shedding? That would be the other option that I can do. And then you can think of any possible combinations, right? You could do, okay, can I do first islanding into those and split those into those 2 chunks, and then I could do load shedding. So really for this case, if we were calculating the reward, this is kind of like after the fact that what the algorithm said that the best thing that we could do was first to do load shedding and then after we did load shedding to do islanding. And that kept 86% of the load being served. So that's not very intuitive for any particular given system. So that's just an example of, okay, if I have this amount of time, what are the strategies that can give me information about how to do that? So that was just an example of that one. And I have one last thing, and then some time for questions perhaps, but the one last thing is just to highlight a little bit more the concept of how we chose those islands. That's also not a trivial problem. In that case, that was a 39 bus test case somewhere in New England many years ago, but it's helpful for us to tell us some Apple simulation. In that case, we just say we're going to split it in half and then again in half. But how do we do those clusters is actually very important too. So one of the other things that we are doing in particular for this project and in research is, can we do that zoning or clustering so that we are actually operating the system, if you look at things like reactive power reserves or voltage profiles, in a way that they will break down somewhat gracefully, right? So if we are operating that system in something that looks already something like in those zones, when they break down, we're not going to have crazy things like loop flows, or we're not going to have very large reactive power swings. In this case, this is the RTS-96 system. We can find the sensitivity of active power with respect to voltage angle. So here what we're trying to do is zoning that minimizes the loop flows, essentially. So if I want to inject a 1 megawatt and send it to Ted, and Ted wants to withdraw 1 megawatt, probably it's not a very good idea that 1 megawatt goes around the room outside and then goes back in. That's, I think in the West Coast we call it parallel flows. In the East Coast they used to call it loop flows, at least for PJM. So if you hear my accent, it's clearly from the East Coast, right? So if you look at that active power sensitivity, in this case the RTS-96 will give us this nice division between flows that will behave very well with respect to active power transactions. It's not very surprising because the RTS-96 test system is basically a copy-paste of the original RTS test system into 3 different islands. So something that's split into here kind of makes sense in the way that they created the system in terms of electrical distance, because it was a 3 copies of that one. So that's one solution. But we also did it for the West Coast. So if we look at saying we're going to cluster that Western interconnection into 8 different areas that they are very close in terms of active power sensitivity, this is the kind of clustering that we will get. So these areas in pink are electrically close, so active power transactions that they're going to happen there, they are going to tend to stay in this area. Then we have another one here, we have another one here, and then we can look at many different details. There's many ways in which we could do this clustering. But here the question that I'm going to leave with you is basically that works very well for active power transactions, but then what happens if we look at reactive power transactions? For the RTS-96 system, if we just look at the sensitivity of reactive power and we look, let's say, at reserves, these areas also give me a really good distribution. And very surprisingly, or maybe not, depending on how you're looking at this, just looking at a different portion of the Jacobian actually gives me a very, very similar partition for the Western interconnection. So this is just purely based on reactive power. There's some areas that merge, but basically this map is good for reactive power. The previous one was good for active power, but you don't have 25 different solutions because we only have one power system at the end that could potentially be breaking down because we have an earthquake. So we need to try to put those things together. So this is some of the ideas that we have. What if we combine some of that active power and reactive power transaction? This one doesn't look like very amazing in terms of drawing, but actually it starts to wrap around very interesting. So it gets this bus and then this set of generators and puts them together with this area because they are behaving somewhat similar. So you can see how it's actually doing interesting things in terms of zoning for potential microgrids that they are not trivial if you're just looking at the distance. So if you combine those two, one way to combine it, we like to put our reactive power with J in terms of phasor. So we do the same thing, just being nerds for a little bit. And if you combine those two, then you can actually say, okay, can we obtain zonings or areas that they're actually good in terms of active power injection, reactive power profiles. And you can look at different things. For example, this area here actually now is a hybrid area that will behave well in terms of both those two injections. Then you have another large area here, and you can start thinking about kind of like zooming in and answering other questions. So that's an open question that we have basically at the end of this project, and that we're going to keep continuing. So if you have any input, we're going to keep working on that. So I want to give a lot of credit to my grad students that they were very hard on this. This is my email if you have a copy on your slides. And also another thing that I'm very passionate about, it's SHIP Oregon, which is the Society of Hispanic Professional Engineers. This is the Oregon chapter. It's the largest Hispanic technical organization in the US, and I'm the president of the Oregon chapter. So if you want to talk some Spanish and see, and you want to hire some really good engineers, just talk to us, see what we are doing in our website. So thank you very much. Yes?
So I'm glad to see your last part there, because one of the things I see the NERC standards doing is trying to make the system increasingly more cohesive, which probably makes it more resilient against small things. But it really seems that we should know in advance how to split it, how to break it apart. I use the analogy of the control joints in the sidewalk. It's going to crack this far and stop. And so it's nice to see that there are some meaningful islands. Perhaps future standards should begin to address how you hold those together when the world is collapsing outside of it.
Correct. And that's the whole idea. What I've been calling them clusters versus islands or microgrids, because the idea with that kind of partitioning is, can we get zones that they are behaving well right now with reactive power reserves and loop flows, but then they are very good candidates to actually become an island and minimize those crazy transitions that might happen. So why operate as two different power systems, which is just the same one under a damaged state? So it's not easy. I mean, that last one, for example, is an open question of how to reconcile all of those different constraints that we have. But we've found good results so far that they behave much better when you run them through some of the bad events. So thanks for that feedback. Yes?
Can you comment on if the Cascadia Subduction Zone happens in like Portland and Seattle and the Northwest loses power, does that affect California? Well,
it will definitely affect, and we have our DC intertie, so there's depending on the time of the year that will happen, it's very likely that we will have a flow going south. So really, I think going back to your previous question, I think it will affect it very much, but if we are treating the system in a way that most of the time there's no crazy long flows that they reach far distances, we're going to be in better shape when we are doing that kind of drastic damages. So a cluster is not going to tell you that all the time you are not really doing any type of transaction, because then you will basically have a microgrid already. However, it's more likely that you're going to be either in good shape or very close to good shape, so that a minimum ramping, for example, is going to get you to a good balance on active and reactive power. So I think you can not really neglect that risk at all times, but you can say, okay, throughout the year, for different snapshots, I can be very confident that this is going to behave better and break down more gracefully. Yes?
I may have missed it, but in your analysis, did you kind of prioritize different loads that you would want to keep on and want to shed, or was it more random than that and just numbers based and match the generator?
In this case, on the RTS 96 case, we just did homogeneous load shedding. So we didn't add more options. Yeah, we did like typical thresholds. Like if you look at the standards, they will say first thing that come out is any hydro pump. Then next thing is this at this frequency. So we just got just normal 5% thresholds and just go with everything homogeneous. However, we have some other results that they have. One of our students, Jinsub and I, we co-advised one student also working on cybersecurity. For that case, we really prioritize loads that might be closer to some of the measurements that we're taking with PMUs. We can do a lot of options. And then those options in this kind of framework will basically add in as different policies. So you could add an homogeneous load shedding policy and then compare it with a high priority versus low priority policy, or close and far load shedding. So it will still work on the same math, but it will be just a little bit more expensive computationally to add more options.
This would be interesting, like say that pink zone, or the darker pink zone, number 4, had all your important loads.
Yeah.
But you in this one it would separate out, with all the generators from the bottom.
Definitely that will work as several options. And just in this example, we say, imagine that we don't have any more knowledge about the system. So just to show that we can actually find solutions that make sense in helping you find that sequence that keeps things connected. But very good point.
I have one question.
Yep.
So Gene kind of purposed one of the previous questions. So is designing a system so that it can be operated in a clustered or microgrid manner, is that in opposition to a goal of trying to make a more interconnected system? I mean, can you do both at the same time? Can you have a system where you're building more connections, but it's also able to operate islanded as well? Can you do both at the same time?
I think you can do both at the same time to a certain extent. So all of those clustering algorithms, they have different thresholds. The original version of that clustering algorithm, we worked on the PJM network. So they say, we want to have this number of clusters because it was like a given number. So we have some sort of tolerance to be kept within that number of clusters. But we could allow things like, okay, really if you want to have an external transaction, we can give a little bit more wiggle room to that transaction. So really if you are allowing for those, you are increasing the chance that something else is going to have to go down. So one way of optimizing that is just do something like a Pareto front with multi-objectives. And that's one way that you can do that. But so I think it's doable. You're going to have to find that Pareto front of what is the sacrifice that you are willing to make in terms of perhaps time of the day versus winter peak, off peak, versus how many long transactions are you going to allow. So that becomes the optimization problem. And I think that's a super important problem. But I think even before that, the fundamental question that I left there as open is, can we even combine those wish lists in a way that it's meaningful for everyone dealing with that power system? Yes?
An interesting offline conversation would be how to take this really cool analysis and compare it to the operational implementation on a nuclear-powered warship. Because we do a combination of failure modes and effects criticality analysis, load shedding. It's all, on a Trident, it's manual. But by design, we have the non-vital bus, the vital bus, the instrumentation bus,
Right.
and the prioritization of loads might not be obvious. One, you got to keep the reactor up, except if you don't, but you got to be able to shoot a torpedo or the missile without a doubt. And so we use the concept of graceful degradation in a combat system. And I think some of this would be really fun to play with in an unclassified manner, of course.
The nice thing is that you can break things on the computer, right? And you don't get in trouble. So we don't have to break anything in real life. So I agree that perhaps the framework will be very similar. And then you can define your different policies as applying to that, basically a microgrid on a ship, right? I've discussed with folks that they work on aircraft. And it's basically a flying microgrid. So it's a similar concept. I think just the policies will change, but you're still going to be playing with how much budget you have for actions and how can you prioritize those. So I think it's a really beautiful mathematical
I
problem.
think it might be able to be extended to the Cascadia event and the coast, and some of the things that you decidedly shed, which you don't want to use the word sacrifice in this case, but you make decisions. We're going to drop this part during this part of the event so that we don't induce more problems, due to system disruption. There are some public aspects of that that are a little hard to explain, but I think it's important as we get into this Cascadia modeling to consider some of that stuff.
Yeah, and I think what you're saying right there is that as you are advancing in that time horizon, you might be able to basically exclude some policies that they are not even a good idea anymore, and you don't want to spend computational time on working on those. That's the same way that if you follow a little bit of artificial intelligence and you see AlphaGo and how it was the first time that the computer was beating humans at Go, it's a similar case. You visually look at the different games that you are playing, and then you say, this is really a crazy, crazy, crazy move. So you don't even spend time on that computational tree going down that route because you have some moves that they are not allowed. So yeah, that's a good point. But that will be for another day, that kind of like AlphaGo and things like that.